Hello everyone, and welcome to the last section in Chapter 4, 4.7, Optimization. This section looks very complicated until we get into it and you realize it's the same type of problems over and over. It's a lot of calculator work and a lot of calculation. So I did all the problems ahead of time, so when I write down the answer, it's just because I plugged the stuff in the calculator, but I'll show you how to do it all. Okay? This is applications in real life, things that I'm going to use calculus for to find the greatest or the least of something. And remember, the big concept here is that maximums and minimums occur when the derivative is 0. So what are we going to do? We're going to read the situation and draw a picture. We're going to determine what formulas we need to solve the problem. And if I have to look them up, I'm going to look them up. Figure out what I have and what I want to find. We're going to use what we have to create the constraint equation and what we want to create the optimization equation. We're going to solve the constraint function for one variable and substitute it into the optimization and simplify. Take the derivative, set it equal to 0 and solve. Plug that back into the constraint to find the other variable. And then check all the critical values to answer the problem and make sure we answer the question. That's a lot. People always ask, is this the max or min? Reality is, you do the same thing. Only at the end do you have to worry. And most of the time, they don't have a max and a min. For example, what's the smallest area I can enclose with 100 feet of fence? There isn't one. Because I could just make 100 feet of fence in a straight line and not enclose any area. But that's not really an enclosed area, is it? In this case, there is no minimum. So I'm not going to worry about the max or min too much. Let's jump right into problems and let's see what we can do. Find two positive numbers that satisfy the given requirements. The sum of the first number and twice the second number is 100, and the product is a maximum. The sum of the first number and twice the second number is 100. This is my constraint equation because I have the answer to it. The product is a maximum, and I'm going to put M there for maximum. That's my optimization equation. I want to find the maximum. Take the derivative, set it equal to 0. But I have two variables. So I come back over here, and I solve for one of the variables, and I plug it into this equation. So now I know that 100 minus 2y times y equals M. Now I'm down to one variable. Let's clean it up a little bit. 100y minus 2y squared equals M. It's as simple as I can make it. Let's take the derivative and set it equal to 0. 100 minus 4y equals 0. This is when I took the derivative. Solve your problem, you get y equals 25. But that's only one of the two numbers. How do I find the original, the x number? Let's plug it back in up here. X equals 100 minus 2 times 25. So x equals 50. There we go. Let's keep going with more practice problems. This is the classic problem that you would see in a textbook. You have 40 feet of fence to enclose a rectangular garden along the side of a barn. What's the maximum area you can enclose? So let's draw a picture. Here's my barn. And here's my fence. What's special about this fence is it only has 3 sides. Why is that? Because the 4th side is up against something. Let's call this side X, this side Y, and this side X again because it's a rectangle. What do you have a limited amount of? You only have 40 feet of fence. So that's your constraint equation. You only have 40 feet of fence. What are the variables going to have to do to give me 40? Well, 2x plus y is equal to 40. That's what I have a limited amount of. What's the optimization? What am I trying to maximize? I'm trying to maximize area. What's the area of this thing? Well, it's a rectangle, so it's x times y. So there's my constraint equation and my optimization equation. Take the derivative and set it equal to 0. but I have two variables, so I can't do that yet. Solve for one of the variables. Plug it in up here. 40 minus 2x is equal to m. Simplify. 40x minus 2x squared is equal to m. Now, I'm down to one variable. How do you find a max? Take the derivative. Set it equal to 0. So x equals 10 feet. That's only one of the two parts. Plug it back in here. Y equals 20 feet. Now let's stop for a second. That's great. We did a lot of good work there. But we didn't answer the question. The question says, what's the maximum area you can enclose? Not, how should I build my fence? So area has got to be length times width. So it's 200 feet squared. The final answer on a multiple choice test would be 200 square feet. Not 10 and not 20, but 200. Remember to read the question and answer it the way they ask it. Okay? Time to get into some difficult problems. What dimensions for a 1 liter cylindrical can will use the least amount of material? So I know I need a can that's a liter, and I want to design it so that it's got the least metal possible. So I need two things. First of all, I need the volume. But I know the volume. The volume is 1,000. What's the formula for volume of a can? Well, if you don't know it, you'll look it up. It's pi r squared h. And that's your constraint equation, because you only have 1 liter, which is 1,000 centimeters. What are you trying to optimize? You're trying to optimize the surface area. Well, if you don't know the surface area of a can or of a cylinder, go look it up. It's 2 pi r squared plus 2 pi r h. And that's what I'm trying to maximize. Take the derivative and set it equal to 0. But I have too many variables. So let's solve one of these. H equals 1,000 over pi r squared. Plug it in here. We're going to get some very complicated numbers here. 2 pi r squared plus 2 pi r h is 1,000 over pi r squared. And that's what I want to minimize, or minimize. That's right, minimize. Clean it up. 2 pi r squared plus 2,000. The pi's will cancel over r is equal to m. Time to take the derivative of this thing. The derivative of this is 4 pi r minus 2,000 over r squared is equal to 0. If you don't believe me, take the derivative of it. How do I solve this? Well, 4 pi r equals positive 2,000 over r squared. Cross multiply, and I would get 4 pi r cubed equals 2,000, which tells me r equals 500 over pi cube root, which is roughly 5.419. And I only know that because I did it ahead of time. So that's one answer. 5.419 centimeters. Now how do I find the height, if that's the radius? I go way back up here, and I plug it in. H equals 1,000 over pi times 5.419, quantity squared. H equals 10.840 centimeters. And again, I did that ahead of time in my calculator. That's a tough problem because you have to know formulas. If you don't know the formulas, you have to get out your phone and Google them and figure out what they are. Let's keep going. What points on the graph are closest to the point 02? What are you trying to minimize here? If you're trying to get the closest, you're trying to minimize. I want to minimize distance. I want to minimize distance. Well, what's the distance formula? It's It's x minus xp, quantity squared, plus y minus yp, quantity squared, is what I want to try to minimize. If you don't know it, you got to Google it. Let's plug in some things we know. I know that x is x minus the x point is 0 squared plus, what's y? 4 minus x squared minus 2, because 2 is the y value of the point, squared equals m. Good news, it's all one variable. It's all x. Bad news, it's really ugly. This is the square root of, that's x squared, plus negative x squared plus 2 squared equals m. This, if you were to square this out and add it, you're going to get x to the 4th. That's minus 2x squared, minus 2x squared, minus 4x squared, plus 1 is minus 3x squared, plus 4 is equal to m. I have simplified it as much as I possibly can. Take the derivative. 1/2, leave the inside b. It's the negative 1/2. Derivative of the inside, 4x cubed minus 6x equals 0. We got to clean this up. 1/2 will cancel out with those two things and make it 2x cubed minus 3x over top of the square root of x to the 4th minus 3x squared plus 4 equals 0. When is a fraction equal to 0? When the top is equal to 0. So 2x cubed minus 3x equals 0. There's lots of factoring, but you always forget the first type. GCF. So what are my answers? X equals 0, or x squared equals 3/2. But I can't leave it like that. That's x equals plus or minus the square root of 3/2. So how many answers do I have? I have 3. 0, square root of 3/2, negative square root of 3/2. But it didn't just ask me for the x values. It said the points. So I've got to plug all 3 of those x values in right there and find the points. So the points are 0, 0. That one's really, nope, sorry, 0, 4. 0, 4. The other ones are positive square root of 3 over 2, comma. If you plug in positive square root of 3 over 2, square it, you get 3 over 2. That's 8 over 2. 8 over 2 minus 3 over 2 is 5 over 2. If you plug in the negative and square it, you get the positive back, so you get that. You get these 3 answers. That's a tough problem, but look at it. Make sure you can do one like that. You'll see it on a quiz or test soon. Last one. A manufacturer wants to design a box, open box, with a square base. So here's my box. If it's square, that means the bottom is the same size, but the height might be different. Surface area of 108 square inches. So that's my constraint. What's the surface area of this box? Well, I've got to build 5 sides. The bottom and the 4 sides around. I don't have to build the top, it's open. The bottom is x squared, and the 4 sides are xy. I want to maximize volume, so my optimization equation is volume. What's a volume of a box? Length times width times height. Well, take the derivative and set it equal to 0. I have 2 variables. Let's plug one in. So y equals 108 minus x squared over 4x. Or you could say that's y equals 27 over x. No, let's not worry about that yet. Let's not worry about that. Let's plug it in over here. X squared times 108 minus 4x over, or 108 minus x squared over 4x. clean it up. That's, one of these will cancel, but one of them will distribute in. 108x minus x cubed all over 4 is m. I don't like fractions, so let's try to get rid of as many as we can. That's 27x minus 1/4 x cubed equals m. That's as simple as I can make it. Time to take the derivative. That's 27 minus 3/4 x squared equals 0. That's 27 equals 3/4 x squared. That's 36 equals x squared. That's x equals plus or minus 6, but it's not really plus or minus 6 because I can't build a box that's negative 6. So it's x equals 6 inches. Okay? That's only half the problem. It wants me to find the dimensions. So one of them is 6. Let's take that information way back up here and find the y value. So y equals 108 minus 6 squared over 4 times 6. Y equals 3 inches. So what dimensions will make the best? 6 inches by 6 inches by 3 inches. Optimization problems look complicated, but they're the same thing over and over. You will have lots of practice problems with these. If you Google optimization problems, you will find a bunch of them online. I did not do a mini lesson for this because it's pretty much the same thing over and over again. That's it for Chapter 4. If you have any questions, come talk to me. 4.8 is really part of Chapter 5 in my opinion, so I'll cover it with the Chapter 5 material. Okay guys, thank you.